If I have any more luck with the computer today. Okay, well, while I'm waiting for that to decide if it's going to work, today we're going to talk about, we're going to start talking about, it's probably one of the most interesting and powerful tools that we talk about in differential equations. That's the Laplace transform. So this it might seem a little mysterious and arcane at first, but it's really not much more than just an integral. The Laplace transform, it's a particular example of something that we call, actually, I want to make that a little. New one. So it's an example of what's called an integral transform. Okay. So an integral transform, it's something that takes in a function. So we'll input a function, and what comes out is another function. So in both cases, this is a function of a single variable. And the way that it transforms the input into the output is using an integral. So it's an integral of something. Now, the form of an integral transform is the integral from alpha to beta of k of st times our input ft dt. So this is how an integral transform works. It takes an input and then it computes this integral to get a new function. This function k, I'm describing things in generality right now, but the specific thing that we're going to talk about is the Laplace transform. So in general, this function k, so we're sort of we're sort of transforming it across this function. So this function k of st is called the kernel of the transform. And this is what determines how our transform works. So it's a function of two variables, s and t. And so what we get for this integrand here, it's a function of two variables, s and t, multiplied by the input function, which is just a function of one variable, t. So that product is now a function of two variables. And when we perform the definite integral, so we're performing this integral and we're just treating s in this expression as if it's some constant. Right? And so the definite integral, it sort of gets rid of that t. We can think of it as it integrates away the variable t. Right? After we've performed this definite integral, that variable t no longer exists in the resulting expression. So what we're left with is a function in just the variable s. So that's how integral transforms work. You take a function of one variable, you multiply it by a function of two variables, and then you integrate away the original variable. You can kind of think when we were doing integrals before and we were replacing the variable with a dummy variable, it's because that variable in the definite integral can be integrated away. And so after that, for example, we were doing the definite integral, but with a variable upper bound. So we were having x as the upper bound. And we used s as a dummy variable. Then what we got at the end was the antiderivative of that function that we put. So that's what happens in a definite integral. This variable that we're integrating on ends up completely going away. So the power of this technique is it lies in the possibility that this resulting function, the function that comes out, is simpler to deal with than the function that we started with. We transform it into something that it carries along all of the information about our original problem, but it presents it in a way that's easier to deal with. And the idea is we deal with the problem in this new domain. We find what information we're looking for in the new domain, and then we go backwards through the transform. So we do some work, and then we come back out the other side to get a solution. So this is called inverting the transform, or if it has an inverse transform associated with it. So a transform that takes the output and turns it back. So that's how these tools work, these tools of integral transforms. So the Laplace transform is one example. And that's the one that we'll talk about, but one you've probably heard of, and it's probably more famous and more used than the Laplace transform is the Fourier transform. These are very closely related. Okay. So in the Laplace transform, and by the way, this is pronounced Laplace, not Laplace. That's something you can tell people at parties. This is named after the mathematician French mathematician Pierre-Simon Laplace. And I don't have the date when he came up with this idea written. But it's named after him, even though a lot of the work was done by other mathematicians. So the kernel for the Laplace transform is k of st is equal to e to the minus st. And so we often write the transform as this script L. And then the input function we put in curly braces. So something like this. So this is a function of s. So we think of this as the name of the transformed function, or the output of this transform. Oh, I should say we had a name for things like this that took in a function and output a function, and we called these operators, right? So the integral was an operator, the derivative was an operator. We were able to chain together derivatives in order to produce operators for our differential equations before. This is another kind of operator. It takes in a function and it spits out a function. So we're thinking of this as the name of the transformed function, and this parentheses s indicates that it's a function of that one variable. The limits for the Laplace transform are from 0 to infinity. We're thinking of this as an integral across the real line, starting at 0 and going to infinity. And we have e to the minus st, f of t, dt. So this is how we get the transform function. Now, oftentimes you will see this written as the transform function is capital F for the sake of not having to write out the script L, curly braces, F, T. That's at risk of confusing it with the antiderivative, which we oftentimes use the capital letter to indicate the antiderivative. So just you should know which one it is basically. Okay. So we often think of t as representing time. And this integral, well, we start from time 0 and we continue to integrate this thing all the way to the all the way out for the entirety of the future. So what does S represent? Well, this takes a little bit of explaining because we really think of S as being a complex variable. So the inputs to F could be complex numbers. And it's confined to a region of the complex plane. Right? We represent complex numbers existing in a 2D plane. They have a real part and they have an imaginary part. And this is called the S-plane. This part of the complex plane that we restrict the S to is called the S-plane. So these S's represent, well, it's only slightly more complicated than this, but they basically represent frequencies of oscillation. Sometimes we call them complex frequencies. So we're using a complex number. If you remember that Euler's formula, e to the complex number t represents a periodic solution if there's a complex part to that complex number, or an imaginary part to the complex number. So in this way, we think of these complex numbers as representing frequencies of oscillation. So just like we might scan along the real line, looking at values of our particular function or how big this function is at a particular time. So this is the time domain. Intuitively, this is how we think about this function. What this transformation does is it transforms this function into something where instead of scanning around for a particular time and looking at how strong the function is at that particular time, we're scanning around at different frequencies of oscillation and looking at how strong the function is at that particular oscillation. So this is called the complex oscillation domain. And when we look at things from this point of view, oftentimes the problem will become a lot simpler. It will change form, and we'll actually look at how that works. Like I said, this is just roughly speaking, but this is the basic idea. Okay, now since the upper limit of our integration is infinity, it might be a good idea for me to review how we deal with integrals where the one of the bounds goes to infinity. So this is just a quick review of Calc 2, but these are called improper integrals by one of those accidents of mathematical history where they call it something. Even though there's nothing particularly improper about an improper integral. We can make these things completely well-defined. Or an improper fraction. Dumb name. I don't like it, but we're stuck with it. So when we write an integral to infinity, going to infinity, so let's say we have this integral like this, f of p dt. The way that we can make this precise is say what we're really doing is we're looking at finite integrals where both bounds are finite. And then we're just seeing what happens if we make this finite bound arbitrarily large. Does this thing go towards something? So if these finite integrals go toward something, and just one thing, of course, then the integral is said to converge to that something. In which case, we say that this expression, this improper integral here, we say that this thing has a value. We assign a value to it. This collection of symbols and letters and numbers, etc. We say that it has some kind of number as a meaning, and it's whatever this limit converges to. Now, in every other case, so whenever it doesn't converge to a particular number, we say the integral diverges. So the mathematical situation being represented by this collection of symbols. We refuse to assign a value to it. We say it diverges. We say that this thing, we're not going to assign a value to. It's not the same thing as saying that we can't assign a value to it. We're just choosing not to. And we call these things divergent. And we kind of set them aside and say that this is not the kind of stuff that we're going to deal with. They're just, they border on not making sense. Now, it's another question whether we can sort of force them to make sense. But in the case of a converging improper integral, then we say that it basically obviously makes sense. It very definitely assign a number to this expression. So that's the difference between these two scenarios. Okay, now some examples. One of the most important questions that we can ask about an improper integral. I'll just go quickly through some examples. These will be illustrative of some of the situations that we'll deal with in Laplace transforms. So the integral from 1 to infinity of dt over t. Now, if we rewrite this as the limit as a goes to infinity, the integral from 1 to a dt over t. Now, the thing inside the integral, this part right here, nope. Just change colors. That's all I have to do. Now, this part right here, this part is a finite integral. It's something that our calculus skills allow us to deal with, and it is in fact equal to the natural log of t. Of course, the bounds of integration are all positive, so I don't have to consider the absolute value. It's just the natural log of t. Now we consider this thing, need to make a little more room for that limit expression, natural log of t. Now, oftentimes you see a bar written on the right side. This is just my idiosyncratic notation. I use square brackets instead. I say this thing is evaluated at the lower one and the a. The limit as a goes to infinity equals the limit as a goes to infinity of the natural log of a minus the natural log of 1, which is 0. So I'm just not going to write that. And this is, we do this, well, it's not so bad, as long as we remember what we're saying with respect to this convergence and divergence thing. We often write this thing as the limit of this thing equals positive infinity. Now, this looks like we're assigning a value to it, but what we're really doing is well, in a certain respect, we can think of it as assigning value to it, but what we're really doing, or what we would be more precise in saying we're doing, is we're saying this thing diverges, but it diverges in a particular way. It diverges towards an arbitrarily large number. If we take larger and larger a's, we keep getting larger and larger values for the output. So it wouldn't be proper, it definitely would not be proper to say that this thing converges, and it borders on saying something that we don't actually mean. We say this thing is actually equal to 0. It diverges, but it diverges in a special way, which allows us to write equals 0. Sometimes it's convenient to say that. Now, something that blurs the lines of what we're doing more, but I think is just as okay as writing this, is instead of writing this thing out as a limit, what I go ahead and do is I just do the integral and plug in infinity as an upper bound. And what I end up saying here is that this thing is equal to natural log infinity. In the back of my mind, I'm kind of saying to myself, this doesn't really make sense because what I'm trying to deal with here is real numbers. Infinity is not a real number in the sense that it's not on the real line. It's not on the number line. But I know basically that if I plug infinity into natural log, I'm getting infinity. So I just write equals infinity. And then if I plug 1 into natural log, it's 0. So this is equal to infinity. And I'm kind of doing a mental shortcut where I'm just skipping that limit expression part. Now, I think this is okay to do. A lot of teachers will sort of say that this is a bad idea because it leads you to the possibility of being confused about what we're actually trying to represent by this collection of symbols that we're writing in a paper. But I think as long as you're careful. Okay. So next example. Oh, this is an example of something that maybe I should just go with the rainbow colors. So it diverges. So we don't assign a value to this expression. Okay. Another example is the integral from 0 to infinity of e to the ct. So if we go through all of the kind of steps of rewriting, that's one of the nice things about all of these rules, where there should be a dt. The nice thing about all these rules of rewriting things in a specific way is that you can kind of think of it as just a mechanism where you're just turning the crank and getting an answer out the other side. Anyway, this is the limit as a goes to infinity of the antiderivative of e to the ct is 1 over c times e to the ct. We evaluate this thing at 0 and infinity. And now we have a variety of cases. So if c is less than 0, then what we have in here is something that as t gets larger and larger, e to that value gets smaller and smaller. It goes towards 0, right? So in this case, what I get is the limit as a goes to infinity. Well, I can go ahead and write this here. The limit as a goes to infinity of e to the c, e to the ca over c minus e to the 0 over c. Well, that's 1, so minus 1 over c. Now, as long as c is negative, what we get for that first part is 0. And so what we get for the whole thing is that this is equal to, write it like this, it's equal to, c is negative, is equal to negative 1 over c. In this case, it converges, and this is the value it converges to. In the case where c is greater than 0, it diverges, and we might easily see it diverge to infinity. So in our sloppy way of writing things, but okay, as long as we're careful in our minds. Now the remaining case is c is equal to 0. And we come up with a problem here because what we have is c is equal to 0, a is, well, basically equal to infinity. And so if we just kind of plugged infinity in for a, then what we see is that this is a 0. We get a 0 times infinity, and we can't come up with a definition for what that should be equal to. Now, if on the other hand, we think of this as a limit where we're taking values and we're looking at what those values approach, then when this is equal to 0 here and this a is finite, then this whole expression right here is equal to, should be a little bit careful. Am I being careful? Maybe there's another way to look. I want to say that this is oh, we have a problem. Which is that if we have c is equal to 0, then we have a bigger problem. Well, we have an equally large problem, which is that we're dividing by 0 in this integral. So we can't do the integral in this way. We have to go back to the initial step and look at what happened before we did the integral, and that's right here. So if c is equal to 0, then e to the 0t is equal to 1. And what we have is just the integral from 0 to infinity of dt, which is going to be infinity. It's going to diverge to infinity. So again, this thing diverges. So we will say that this thing only converges when c is less than 0, otherwise it diverges. Another example. I'm going to go through these quickly, so we have time to actually talk about the Laplace transform. Okay, so t raised to some negative power p, or raised to some power negative p. Now again, if p is equal to 1, then we've already seen that this thing diverges. That was our first example. Diverges. So that was our first example. So we're going to look at the other case. Now, when it's not equal to 1, we can do the integral, which is the step I should have pointed out in the beginning of this one. Anyway, we get p to the negative p plus 1, so we'll write that 1 minus p divided by 1 minus p, evaluated at 1. And our upper limit is a, and we're taking that a going arbitrarily large towards infinity. And so what we get is if well, let's go the other way this time. If p is less than 1, then this 1 minus p is greater than 1. And so as t gets arbitrarily large, then that thing goes to infinity. Maybe I should do that other step that I did. So this is the limit as a goes to infinity of 1 over 1 p to, or a to the 1 minus p minus what we get when we plug in 1. It's just 1 minus p. So this thing, like we said, if p is less than 1, then t to the 1 minus p gets arbitrarily large, and this thing stays exactly the same. So infinity minus a finite. Now in the other case, if p is less than 1, then this thing goes towards 0. As a gets bigger and bigger, a to the 1 minus p goes towards 0. And what we're left with is negative 1 over 1 minus p, which is, we can just write as 1 over p minus 1. So again, we get a region where it diverges and a region where it converges. Everywhere in that region it converges. Okay, so one of the things that makes the Laplace transform so powerful, well, there's a lot of things that make it really powerful, but one of the most important, it's up there in the list of important, is that it allows us to deal with driving forces that are not continuous functions. So since we're going to be dealing with a class of functions larger than the continuous functions, we should review that class very quickly, and that is piecewise continuous functions. So these are functions where if we take a particular interval, alpha to beta, we don't necessarily need to include the endpoints, but that's okay. So if we take this interval on which the function is defined, alpha to beta, and we split it up into this collection of points where we cut it, right? So our left-hand side of the interval is t0, and then we cut it at t1, then we cut it at t2, and then we keep cutting it all the way up to tn, where tn is the right-hand side of our interval. So we've taken this from alpha to beta, and we've chopped it up into, this is equal to t0, and then t1, t2, t3, t4, and t5. Then if this thing is piecewise continuous, then what we have is that on each of these intervals, on each subinterval, ti to ti plus 1, let's say we'll call this function f. So f is continuous. So that's one criteria, and the other one, well, that's the piecewise continuous part. It's continuous if you chop it into pieces, and a finite number of pieces, and it's approaches a finite value as t approaches an endpoint from either side. So if we approach t1 coming from this side or from this side, either way, we're approaching a finite number. They don't necessarily have to be the same finite number, but it has to be finite. So here's an example. So let's say this is 1 here and 0 here on the y-axis. So let's say we have a function that as we go along, it's 0 all the way up to alpha, and then it jumps up to 1, like this, all the way up to T1, and then it drops back down to 0. Okay. As we approach these endpoints, we come in from this side, we're approaching 1. As we come in from the right-hand side at T2, we're approaching, or at T1, we're approaching 0. So these limits don't have to match. That's fine, just as long as they're finite. So we chop it up into pieces. It's continuous, and the endpoints are finite at each of those points. Now, of course, on this side, we can only approach from the right side, so we don't worry about the left. We could have something. Here's an example of something that's not piecewise continuous. If we were to include a piece over here that went up to infinity, that would not be piecewise. Okay. So we can integrate piecewise continuous functions. We integrate from alpha to beta, ft dt. We just integrate each of the pieces. So we go from T0 to T1 of t dt plus T1 to T2 f of t dt, all the way up to Tn minus 1 Tn f of t dt. So to integrate a piecewise function, the pieces are continuous. So each of these pieces, the integral is well defined. Now, sometimes we have the case that if we look at a piecewise continuous function, it's difficult to see, or if we're looking at an improper integral of a piecewise continuous function, then it might be difficult to see how we can rewrite that integral in terms of elementary functions that we're used to, so we can know how to evaluate that limit. So sometimes we may get into a situation difficult. So what we can do is we can compare our integral to some other integral that's easier. This is sort of like the comparison function, but it's for integrals instead of. So suppose that we have that f is piecewise continuous, and we have that well, it's at least piecewise continuous once we get past a certain point A. And the absolute value of f at particular input t is bounded below by g of t for all t greater than some m. So once we get past a certain point, then we have that our absolute value of the function is always bounded below. We have our function. Maybe it looks like this. And we have our g function looks like this. But from then on, I don't know why it's doing that kind of wavy. Anyway. So it may not be bounded everywhere, but once we get past a certain point, it is bounded by this g. So maybe this is our m right here. Okay. If the integral from m to infinity g of t dt converges, then the integral from a to infinity of f of t dt converges. We don't get what the value that it converges to, unfortunately, but we at least get that it converges. So we're not going to prove this rigorously, but it's kind of straightforward to see why this should be true. there's an area under the curve here, and this area under the curve is, sorry, wow, made a big mistake. I did the second part of the theorem before I did the first part. Let's redraw this. Okay, so we have our function here, and then our green function is sometimes below. This should be a bounded above. So now from this point on, bounded above. And that's what I want to say. The area under this green area converges, it's finite. And so this black area under here, it's smaller than the green area, right? So it must be finite as well. But then we've got this area over here where it doesn't bound, but this area, because it goes from A to M, this is also finite as well because it's piecewise continuous in this region. So it must be finite. Okay, conversely, we have the other direction. If we have that f of t is greater than or equal to g of t is greater than or equal to 0. So now we have this f of t, the area is bigger than g of t. And the integral from m to, at least if we get to some point in this condition is true. And the integral from m to infinity and the integral of m to infinity of g of t dt diverges in the corresponding integral for f of t diverges as well. And you can see the same thing. The area under the curve of f of t has to be bigger than the area under the curve of g of t. So if one diverges, the other one. Okay. Now, using this, we'll be able to say if a particular Laplace transform exists, and otherwise if that integral converges, and for what particular values of s it will converge. So that will define our S-plane. All right. So the way we're going to use the Laplace transform, well, let's come back to that. Let's actually give some facts about it before we start trying to use it. So we'll apply this, what we've said already. Suppose f is piecewise continuous. On the interval 0 up to a, or arbitrarily large a. 2. We have that the absolute value of f is bounded by an exponential. K is some constant. So for, say, for all t greater than or equal to m, and some for all, I would say for some k, a, m. So if we can pick an exponential with some rate of growth and some constant multiplied by it, and we can bound our function f by that function. Well, this function converges. Well, this thing converges if we make a to be negative. And so we say then the Laplace transform of f of t s, otherwise known as capital F S, exists. In other words, the integral converges for all s with the real part of s greater than a, and that's this a right here, the growth rate of our signature. Because we're going to be multiplying this by e to the minus s. And so if this s is bigger in the real part than a, then you get an exponential growth being canceled out by an exponential decay. Now, I need to say a quick point about this real part of s. This is the real part of s. Now, for this, for all the stuff that we're going to do with the Laplace transform, we're not really going to have to care about the fact that the input to the transformed function, capital F, can be a complex number. All that we're going to use is real values of s. And so we can rewrite this and just say s is greater than a. So we're looking at this exists whenever s is greater. But in the back of our mind, remembering that this is a broader thing. Okay. Now we've made it. We've got this defined. This criterion 2 bounds our function, the growth of our function by an exponential. And so we say that this thing is of exponential order. Just quickly describing some of the meaning behind these things. So if it's bounded by an exponential, we say it's of exponential order. And as an example of something that isn't of exponential order, e to the t squared. So this is not of exponential order. Okay, now we've gotten to the point where we can compute some Laplace transforms. That's what we'll end with today. So the first one, I'll try to do these quickly because we're getting a little low on time. The Laplace transform of 1, so just the constant 1. So this is just the integral from 0 to infinity, e to the minus st dt. This is equal to negative 1 over s times the limit as a goes to infinity of e to the minus st evaluated at 0 and a. Now I'm just going to do the kind of trick where I just plug in infinity, so e to the minus infinity, that's 0. Remember all those times I said e to any value is never 0, and so we can divide both sides by that e. Not the case if you include negative infinity. So this thing comes out to just be 1 over s. So that's our first Laplace transform. It turns 1 into 1 over s. Okay, what does it turn some other thing? What is the Laplace transform of e to the at? Oh, I should also say this is bounded by e to the at for what? A. Well, we only care about well, we can say for any a, but it's definitely bounded for e is equal to. We also have a constant that we can play with up front, but it won't be necessary. For a is equal to 0, this is equal to 1. And so we can say a is equal to 1. And it's definitely bounded. 1 is bounded by 1, right? 1 is definitely less than or equal to 1. So this is defined for s is greater than a, which is 0. Or the real part of s is greater than a. This is an important part of the Laplace transform. We need to know what the s-plane is. That's our first example. Second example, the integral from 0 to infinity of e to the at, e to the minus st dt. So this is the integral from 0 to infinity of e to the, I'll write this as negative s minus a t dt. The reason I did that will be, well, it'll be clear kind of immediately. all that we have now is that the negative st is replaced by, the s is replaced by s minus a. And so we get the exact same thing here, replacing s with s minus a. So this is equal to 1 over minus a. And so we have, this exists when s minus a is greater than 0. In other words, s is greater than. So that's the transformation, the s plane. The real part of s is greater than a. Of course, we only deal with the real. We don't. The real part is the whole thing. Okay, now here's an interesting function. 1 and e to the at are both continuous functions. There's no discontinuities everywhere. So let's define a function that does have a discontinuity. So our function will be 1 if t goes from 0 to 1. Actually, let's not include 1. Let's give it some other value. Let's say it's 50 whenever t is equal to 1. And we'll say it's 0 when t is greater than. Now, f is piecewise continuous, bounded by 1 times e to the 0 t, which is just 1. Definitely bounded by 1, as long as we get past a certain point. Well, there's this 50 here. The 50 actually doesn't matter. Well, we only care that it's bounded after a certain point, but if we ignored that single point that's by itself, then it would be bounded for the whole region that the function is defined. Let's see what we can do with this. First of all, we know that the Laplace transform of f exists for s greater than our rate of growth here, which is 0. So we know it exists, but we can do better. We can actually get it. So this is a piecewise function. So the Laplace transform of f equal to the integral from 0 to infinity of e to the minus st ft dt. We'll split this up along our points that we break up our interval. So this is the integral from 0 to 1. Now on that region, this function is just equal to 1. This is e to the minus st dt plus the integral from 1 to infinity of 0 dt. So this is just 0, or just 0. So the integral here will just be equal to this. And notice that 50 there, because it's right at the endpoint, and it's just that we think about the area that it contributes a rectangle that's a height of 50 and a width of 0. Contributes no area. Okay. So what is this integral? This is equal to so I don't have to think too much. I'll just write down. I've already worked it out. So I know what it is. And it's equal to this. So the Laplace transform, now we have the Laplace transform of a discontinuous function. It's piecewise continuous, but it's not continuous. So we would have had a lot of trouble dealing with this based on the methods are undetermined coefficients or integrating factors, or what was the other one? Variation of parameters. We would have had difficulty with all of those. Laplace transform, however, transforms this into something that's very nice to deal with. And also we know where this is going. Okay. I apologize if I run over a little bit today, but I want to get to these examples. I want to move on to the next topic tomorrow. Okay, what about sine of a sine function? Well, this is equal, if we're going to go ahead and give this a name, it's going to be f of s, and you'll see why soon. But this is the integral from 0 to infinity of e to the minus st sine of at dt. And you might remember this example from way back when, but we'll go through it again. This was it was just a fun exercise at the time, but now it has a practical importance. We're going to integrate this thing using integration by parts. I'm going to make my u be sine of at, and my dv will be e to the minus st dt, which makes du cosine, a cosine of at dt, and our v is negative 1 over s e to the minus st. Just derivatives and integrals. So this integration by parts tells us that this is equal to uv sine of at times negative 1 over s e to the minus st, evaluated at 0 and infinity, fully evaluated at 0 and a, as a gets arbitrarily large, but I'm going to use a little trick, minus v du, the integral from 0 to infinity of v du. I'll pull the constants out in front first. That's negative a over s. And we've already got a negative, so this becomes positive a over s cosine at e to the minus st dt. Now, this thing right here, when we put infinity in for t, we get 0, and sine is always bounded by it's always bounded by 1 and negative 1. So it's some finite number. So this is 0 times some finite number, so it's 0. And then if I plug in this 0 into sine here, well, if I plug it into here, I get a finite number. Plug it into sine, I get 0. So it's 0 minus 0. So this part right here is 0. Just left with this. Okay. The integration by parts one more time. Looks like it would go on forever. But if you remember, it doesn't. E to the minus st dt du is equal to negative a sine of at, and v is equal to, again, negative 1 over s, e to the minus st. And there should be a dt. Okay. So uv is cosine at, negative 1 over s, e. Sorry, I'm totally forgetting this factor of a over s. I want to forget that. So that's a over s divided or multiplied by all of this. So now I'll write my cosine at times negative 1 over s e to the minus st, evaluated at 0 and infinity, minus the integral of v du. So now I get negative a over negative s, so that's just a over s. So this time it stays negative. And I get sine of at, let's write it in the other order, e to the minus st sine of at. And you'll notice that this integral right here is just f of s. Yep. So what we end up with, well, let's figure out what this thing is first. If I plug in infinity, well, cosine is bounded. This thing goes to 0, so I get 0 there. Plug this in here, I get a 1. So I get 1 times 1 minus s. Plug in a 0 in for cosine, I get 1. So this is negative 1 over s. Glance at my notes. minus A over S times f of S. And this is equal to f of S. Now distributing out, I will get minus A over S squared minus A squared over S squared F. For the simplicity of looking at this, I will get rid of the of S part. So we've got F is equal to negative A over S squared minus A squared over S squared. So I'll add this part over to the other side. I will get 1 plus A squared over S squared F, which is of course equal to S squared plus A squared over S squared, getting common denominators, times F is equal to negative I've ended up with a, oh, right. This was the lower bound, so it should have been subtracted. So this 1 over S is positive. There we go. So this is equal to A over S squared. Now dividing both sides by this thing, dividing it over to the other side, I get F is equal to, these S's cancel out, A over S squared plus A squared. Yep. Yes. And we already know this thing is bounded by 1, which is equal to E to the 0. It's an E with a 0 growth rate. So this thing is valid for S greater than 0. Now one last little piece. How much over am I? Quite a bit. Okay. Now let's look at what happens if we look at the Laplace transform of the linear combination of two functions. Well, this is equal to the integral from 0 to infinity of C1 F1 of t plus C2 F2 of t. All of this times e to the minus st dt. If I just distribute that e to the minus st out, split this into two integrals, then pull the c's out in front, I get c1, the integral from 0 to infinity, f1 of t, e to the minus st dt, plus c2, integral from 0 to infinity, f2 of t, e to the minus st dt. And now you'll see that this has been split up into two Laplace transforms. So this is c1 times the Laplace transform of f1 plus c2 times the Laplace transform of f2. So not only is L an operator, it's a linear operator, which is an incredibly useful fact, and will give us our very last example for the day, which is the Laplace transform of 5e to the minus 2t minus 3 sine of 4t. Okay. Now we can rewrite this thing using linearity as 5 Laplace transform of e to the minus 2t minus 3 times the Laplace transform sine of 4t. And we have these Laplace transforms already computed. So this one is 5 times 1 over s plus 2, and this is valid whenever s is greater than -2, right? Because e to the minus 2t is bounded by e to the minus 2t. So it's valid when s is greater than -2. And the second part, this is minus 3 times a, which is 4, over s squared plus a squared. So we can just write this as 5 over s plus 2. So this was valid for s greater than 0. So 5 over s plus 2 minus 12 over squared plus 16. Now, because this part is valid for s greater than -2, and this part is valid for s is greater than 0, then we take the smaller range, the one where they're both defined. And so this thing is defined over s greater than 0. So there's our input, here's our output, and here's the s-plane where it's valid. Okay. Now I'll stop doing examples for today. I do want to say one thing about the text for the class, which is that I've been really sort of annoyed by the fact that there are so many typos in these texts. And when I got to the Laplace transform section, it was actually things that just weren't even correct, like just wrong statements, worse than typos. So what I have started using is what I was going to use at the beginning of the semester before somebody talked me out of it, which was the traditional Boyce and DePrima differential equations textbook. If you just Google Boyce, DePrima, D-I, Prima, then you'll find this book. And there's editions of it that are, I mean, you can find it PDFs for free on the internet. That's the one that I'm going to be working from. If you can translate your way out of typos in the notes, then by all means look at those as well. But Boyce and DePrima is sort of the standard textbook that people have been using 100 million years. That's what I'm going to go with. So that's it for today. If you have any questions, I'll stick around. Otherwise, see you tomorrow, Tuesday.